Okay, so for the Riemann sum, remember you're looking at the area of rectangles under the curve. So a rectangle is length times width. To figure out the width of a rectangle, you take you're taking going from 3 to 5. All right, and you're dividing it up into 3 equal subintervals. So 1, 2, well, that's kind of equal. All right. So you add or you subtract these numbers and then divide by 3. So the width is 5 minus 3 divided by 3, or the width is going to be 2/3. All right, so remember, whatever this curve does, it's going to do something crazy like that. You're going to connect the left side of the rectangle. All right, so the left side. I think I need one more rectangle. No, I'm done. It's just not divided up nicely. So if you start at 3 and then add 2/3, that takes me to the next part here. So get everything in terms of a common denominator. So 9/3 is 3. So add 2/3 to 9/3, that takes you to 11/3. Add another 2/3, so I'm just measuring off my width. That's 13/3. And then add another 2/3, that takes me to 15/3, which is 5. So you got to end at, where you're supposed to end. So now I want to know what's the area of these rectangles. So it's this height times that width. Well, I know what the width is. The width is 2/3. The height is the function evaluated at that point. So the function was natural log of 3x. So if I plug in a 3, that's going to tell me how high up the y value is. So 2/3 times whatever natural log of 9 is. And it's saying that you don't have to evaluate your answer, you're just plugging in numbers. So cool. Then we go to the next rectangle. So it's again the width times the height. So the height, now we're going to do 11/3. Plug that in for x. So natural log of 3 times 11/3. All right, and then to the next rectangle, it's the width is 2/3 times, and then to get the height, you always go back to the function and plug in that x value for that. So it would be 3, natural log of 3 times 13/3. And then, so it's 2/3 natural log of 9 plus 2/3 natural log of 11 plus 2/3 natural log of 13, I believe. All right, and then is this a underestimate or an overestimate? Well, it looks like, according to my picture, this would be an underestimation. If it's an increasing function, which I think it is, you notice that your rectangles are below. Usually on a left, you underestimate, and on a right Riemann, you overestimate, but that's just kind of a general rule. Let me double check here on my answers. Yeah, he just factored out the 2/3, but whatever. Okay. So I would predict that you're going to have either a left or a right. Now, if this had been a right Riemann, then you don't start with the first number, you start with the second number and end on the last one. So remember, you're connecting up the right sides. So if it were a right Riemann, kind of just a rough sketch of it, you'd still start at 3 and end at 5, and you'd still have the 1, 11 thirds, 13 thirds, 15 thirds, and so on. But your right side of your rectangle touches, and then it goes over. So your right side touches, and then you go over. Right side touches, and then you go over. So when you do this one, you're not starting at the height of 3, you're starting at the height of 11 thirds. So it's still a width of 2 thirds, but it'd be natural log of 3, and then the right one is always going to end on the very right number. The left is going to start with the very left number. Okay, so 3, and then we do times 11 thirds. And then the same thing, 2 thirds, natural log of 3 times 13 thirds, and then 2 thirds, natural log of 3 times, and then the last number 5. So a right Riemann ends on the last number, the left Riemann starts with the first number. Okay? And it helps to kind of draw in the boxes. This is going to overestimate it, and again, this is a really bad drawing, but all of your rectangles are kind of over on the right Riemann. All right, what else do we have? Flipping through pages. Those are the solutions. Okay, so for problem number 5, let me minimize this. All right, so for problem number 5, find the area, so that's an integral of the region. So you're integrating from lower limit to upper limit of 7x over 3x squared plus 4dx. All right, so again, you can see this is an 8-point problem, which means you're going to have to do a little bit of work. Which in this case, in order for you to integrate this, you're going to have to do a u substitution of some sort. And notice where the degree is bigger is on the bottom. So that's generally the thing that you want to do the u substitution for. So if I let u equal 3x squared plus 4, then take the du, and then the derivative of this, the derivative of u is du, the derivative of this is 6x dx. All right, so now this is where I kind of do it a little different than your dude. I leave the limits of integration. I don't fool with those, or I just don't write them down. Don't worry about it. I see an x dx, which is cool, because I have an x dx here, but I have a 6 in front of it. So I'm going to have to divide off the 6 to both sides. So when I put in du for this, the 6 is going to go down below. The 7 is going to come out front, du, and then this 3x squared plus 4 is just u. So then you're going to integrate du over u, which I believe is, isn't that the natural log? I think, of u. I'm looking real quick. Yeah. So this is 7, 6, natural log of, but now take out the u and put in your 3x squared plus 4, and then you can integrate it from 2 to 5 now. Okay. And then just plug in your 5 minus, and then plug in your 2, and bazinga. Okay. Problem number 6 is a lot like the one that I just showed Madison. Displacement is position. So to go from velocity to position, you have to integrate. So for that one, you're just integrating from 0 to 4 of your function. Don't forget to put the dt on there. All right, and then you go ahead and you happily integrate that. Add 1, divide, add, and then evaluate. But this total distance the object travels, that's the one you have to pay attention to. Where's the x-intercept of this? This is a parabola, and you want to find the x-intercept because, you know, it's a parabola that opens upward, and you can kind of plot a couple points. At 0, it's going to be 0, and at 4, 2, 3, 4, if I plug in 4, 16 minus 8 is 8, so it's way up here. But like at 2, it's going to be at 0. So at 1, it's down here. If I plug in a 1, 1 minus 2 is negative 1. So you can see it kind of does a zoop, and then we're going to 4, so 16. Oh, we got it up here at 8. So you integrate, like if it's below, it's going to have the minus in front from 0 to 2. And then you can go ahead and put your function in, t squared minus 2t dt plus, and then above from 2 to 4, it's just above, so it's positive, t squared plus minus 2t dt. And then you integrate each of those individually.